This video is about uh, revising notes for year 12 static electricity topic. So first of all, we will look at the electric force and electrical potential energy. So if there are two plates, one is positively charged and one is negatively charged, and there will be constant electric field between them. The strength or the size of the electric field depends on two things. It depends on the voltage and the distance between the plates. So if we look at this equation, if voltage is increased, electric field will increase, or we can say electric field is directly proportional to the voltage between the plates. And electric field is inversely proportional to the distance between the plates. That means if distance is increased, then electric field will be weaker. Now, unit for electric field is voltage is in volts, and that is in meters. It is volts per meter. Direction is always from the positive towards the negative of the plate. Now, if we place, say, for example, an electron in between the electric field, so that electron will experience a force, and the force will be in the direction that is opposite to the electric field. However, if it was a positive charge, then obviously it will experience a force in this direction, or if it is free to move, then it will move in this direction. Now, this force on this electron or any charged particle depends on the electric field strength. So if electric field is stronger, force will be larger, and it also depends on the size of the charge. If charge is a bigger charge, then force will be more. Next thing we will be looking at is how an electric field can be used to accelerate electrons. And quite often in your TV sets or cathode ray tubes, electrons are accelerated by the use of electric field. So let's say that there is an electron which is right in the middle here. So if it is free to move, then it will move towards this positive plate. And in doing so, it will be gaining speed. It will be accelerating because whenever there is an unbalanced force, there will be an acceleration. So its speed will be increasing, or in other words, its kinetic energy will be increasing. Let's say that this electron was held over here at this end near the negative plate. Now, to hold it over here, we will have to apply a force, or something will be holding it, otherwise it will move in this direction. So that means if an electron is stationary here, it has got some what we call as electrical potential energy. As soon as it is released, it will move in this direction, and electrical potential energy will change into kinetic energy. So an electron can be accelerated by using electric fields. And how much will be the size of the electrical potential energy? Now, so if this electron moves from here to there, then electric field is working on it. And how much is the size of the work done? Work done will be force times distance. So if it was here and it moves a distance d, then work done will be force times distance. That's written over here. So work done is equivalent to electrical potential energy, and it is equal to electric force times d. Now we already know that electric force is E times Q. So if we replace that with this one, work done is equal to EQ times D. Or from this equation, we know that E times D, so if we make V the subject of the equation, that V will be equal to E times D. So this voltage, E times D, is replaced by that one, or work done or electrical potential energy is equal to V times Q. So, and then electrical potential energy changes into kinetic energy. Or in other words, what we are saying is that when an electron moves from here to there, then electrical potential energy is E times Q times T, as was the equation down here. So electrical potential energy changes into kinetic energy. If you want to move the electron backwards, then you will have to apply external force, and then kinetic energy will be changing into electrical potential energy. It will be opposite for a positive charge. So if a positive charge is held here, you don't have to apply force. You will have to, if a positive charge is over here, then to move it from here to there, you will have to apply some force. And in doing so, if you move it from here to there, it will gain electrical potential energy. Or in opposite direction, the positive charge will, electrical potential energy will change into kinetic energy. And from the conservation, law of conservation of energy, all that energy is changed into electrical potential changes into kinetic or vice versa. Another thing that we look at this one is when a charged object is held stationary between an electric field. So let's say this plate is positively charged and this plate is negatively charged, and this is the famous Millikan oil drop experiment. So if a charge is held stationary here, that means forces acting on the charge are balanced. Now gravity force will always be acting downwards, whereas, so that means there must be an equal force which is acting in an upward direction if this charge oil droplet is stationary. And that is the electric force. And electric force is equal to E times Q, is the electric field, and Q is the charge on this object. So, and charge does not have to be stationary. It might be moving with a constant velocity, upwards or downwards. Even in that situation, the forces acting on the charged particle will be balanced. Now, if it is, let's say it is stationary and these forces are balanced, then if this is the positive plate and this is the negative plate, that means this charge will be electric forces upwards, so it must be a negatively charged object. In terms of equation, gravity force is equal to electric force and mg is equal to E times Q. So using this equation, we can calculate the Q is the charge on the oil droplet, is the electric field, G is the gravity, which is 9.8, and m is the mass of the oil droplet. So using this equation, we can find the charge on the this oil droplet, and that was the famous experiment. A ratio of charge to mass was already calculated by the earlier scientist. So by doing this one, Millikan calculated the charge on an oil droplet, and that charge came out to be 1.6 times 10 to the negative 19 coulomb. And it is like a quantized value or a discrete values. So all the charges that he calculated were either a multiple of 1.6 times 10 to the negative 19. And so he concluded that this must be the basic charge on an electron. And obviously protons have got an equal charge, so they have a positive charge. So thank you for watching this video. And that's all for today's video.